Live on WFLA Now. With a specialized degree in climate, Chief Meteorologist and Climate Specialist Jeff Berardelli is pioneering the way we look at climate and extreme weather. Welcome to Jeff's Climate Classroom, powered by ArmorView Window and Door.
All right, thank you everybody for joining me here. We have an exciting show to talk about today because I don't know if you remember this, but about a week or so ago, maybe a little bit more than that, we had a wicked fast jet stream in the eastern part of the United States, mid-Atlantic area, at about 265 miles an hour. I'm a meteorologist, I'll tell you, that's really fast. We don't typically see them quite that fast. And because of that, there was a transatlantic flight that was able to get from Newark to Lisbon, Portugal, an hour earlier than it should have. It reached a maximum wind speed of around, a maximum flying speed of around 835 miles an hour, which is insane. So it really propelled them across the Atlantic. I would not have wanted to be on a flight trying to go against that, the opposite way across the Atlantic. So what I want to do is, first things first, I want to bring on my guests today. The first one is Dr. Tiffany Shaw. She is an expert in this particular field. She is a climate physicist from the University of Chicago in the Department of Geophysical Sciences. Thank you, Dr. Shaw, for joining me.
Thank you so much for having me.
And the other person that you see on the stream is Val Simpson. She is a WFLA weather anchor and also climate curious, I like to say, because she's always asking me questions about the climate. So we bring her on the show because she's always got really interesting takes on these topics.
That's right, Jeff. Super excited. Thank you, Dr. Shaw, again for joining us today. Also, I want to remind everybody, I'm not here alone. I brought my trusty buzzer. Let's see if we can. Can you guys hear that?
I think they can because I just turned off the surround sound on Zoom so that it doesn't cancel out the ambient. I don't know if you know that at home. On Zoom, if you don't want to cancel out the ambient sound around you, you can actually turn that off.
I love learning about technology too, so that's great.
Yeah.
But yeah, just in case, I want to make sure that we're able to understand, just the normal folks out there are able to understand what's going on today and what we're going to be talking about. So every once in a while I might buzz, but I promised Dr. Shaw I wasn't going to buzz her because I don't want to be rude,
well,
but I am
fair.
buzzing Mr. Berardelli.
That's unfair. I feel like that's biased. But
also, I'm going to keep track of any questions that you guys have for on Facebook also. So for Dr. Shaw and Jeff Berardelli as well. So I'll keep track of those for you guys. And yeah, Jeff, take it away.
All right. So what I want to do here is I want to put up a board to show you just how crazy this flight was. So United Flight 64 went from New York City to Lisbon, Portugal. It was flying at 835 miles an hour. Now, we've seen a lot of these flights challenging records. We don't really keep records of how fast flights are going, but everybody agrees it's either a record or near a record, and we've been seeing at least a few of these flights that have been doing this over the past couple of years. Again, the flight normally takes about 6 hours and 40 minutes. Instead, it took about 5 hours and 40 minutes. So that in itself is very interesting. So I want to bring you both back up. Dr. Shaw, your research has to do with the strength of jet streams and how, as the climate has warmed, and it's warmed substantially, we are seeing potentially some of these jet streams in certain cases to strengthen. So before I ask you that, I just want to say that as you know, Dr. Shaw, there's a ton of confusion in climate and weather circles and the general public as to whether climate change is weakening the jet stream, making it more wavy, or strengthening it. So can you add some clarity? So first things first, can you talk about the research that deals particularly with this?
Okay, so this is, as you said, a very rich and important topic, as the jet stream controls many things maybe some of us are not even aware of. But what I want to speak to is this question of, how does climate change affect the fastest winds? Because it was in part motivated by these record-breaking events that were reported, that we started on this research question. And really, this is kind of the crucial thing in climate science. In order to be able to detect the signal of climate change, we need to understand what we should expect. And so when we asked the question, what will climate change do to fast winds, independent of whether or not that's already happening, what we found in our research was that the fastest jet stream winds, so those winds that occur very rarely but are, as you say, exceeding 200 meters, 240 miles per hour, will be increasing at a rate of 2% per degree of Celsius in the global mean. So that's global mean warming in degrees Celsius. And we did this by combining simulations of the Earth's climate. These are physics-based predictions, not unlike weather predictions, but over a much longer time scale. And these predictions showed us this was the rate of increase. But as in most of our research, we wanted to also understand why was it this 2% and not a different value, and obviously what kind of factors were controlling it. So that bring us to thinking about these questions you were asking before also. What is the physics of the jet stream? Why is the jet stream? Why does it exist? Why does it sometimes exhibit faster values or slower values? And so we dug into that based on our understanding from these physical principles. And so maybe to break it down, and I might get buzzard here, but the
well, wait a
point
second.
of
She told you she wouldn't
jet
buzz you,
stream.
so you should be okay. But yeah.
Okay.
So far, we're good.
So the jet stream, of course, is a fast-moving current of air, and one of the confusions potentially is there's different jet streams at different altitudes. So what I want to start with, because it was our research in particular, is the jet stream where the winds are fastest, which is about 9 to 16 kilometers above our head. This is a ribbon of air or a river of air that's quite extensive in the horizontal, 100 kilometers, but quite narrow in the vertical, only a couple kilometers. And this jet stream exists because of contrasts of air density and temperature. And let's think about that to start with in the latitudinal direction, where the air near the equator is very warm and moist. It has much lower density than the air at the pole, which is very cold and dry. And if you think of these as different columns of air, where the column of air near the equator is much taller because the air is taking up more space, it's a lot lighter, whereas the column of air over the pole is much shorter. This difference in this case, altitude, or one can think of it as pressure at the top of these columns, is going to introduce forces that move the air from the equator to the pole. So that's what gets the air accelerating, which is part of what would underlie the jet stream. But then the second piece of this puzzle is that we're on a rotating planet, or the winds are represented on this rotating planet, and we have to deal with the fact that there are forces involved there that deflect the winds that are accelerating toward the right in the northern hemisphere. So that would be from west to east.
Hey, Val.
So long story short,
called the Coriolis force.
The
Coriolis.
Coriolis.
Exactly.
Remember, I'm going
Yes.
to test you at the end of the broadcast.
Okay, I got you.
So long story short, it's about the contrast. So if there's a contrast of density and temperature, we should expect a jet stream. So that's what started the research. And then the question becomes, how does climate change affect the contrast? And that's where one has to know where the contrast is changing. And this is, I think, part of the source of the confusion in the community and in the media and in the general public, because climate change can change the density in different places due to different effects. One of the very well understood effects of climate change is that while there is global warming, when you look at the spatial pattern of that warming, it is in latitude largest over the poles, particularly in the Arctic. We see it observed right now. We know why it has emerged. What happens in a warming planet is you would melt ice and snow, which is tending to reflect sunlight and therefore not absorb it. And when you melt that, you have a darker surface underneath. So you get this enhanced warming because of that melting. And so the Arctic is warming faster. And of course, by doing that, it changes the density. But that would tend to reduce the contrast because you've warmed where the air was more dense. So you've made it slightly lighter in that polar region. And so in that case, near the surface, you would have this expectation at these lower altitudes that the winds would slow down if you just follow through that thought experiment. So that's a well-known effect. There's been many papers written about that.
So can I just stop you for 1 second?
Yeah.
So basically,
Sure.
the idea of a wavy jet stream seems more plausible at the lower levels, lower altitudes, than it would.
But we're not talking about waviness yet. We're just talking about strength.
Right. So slower, a possibly slightly
Yes.
slower jet stream because of the way that the Arctic's warming versus the way the
Yes.
equator's warming
Mhm.
at the low levels. Okay.
At the low levels. So but again, the jet stream it's apparent at different altitudes. In our paper, in our work, we had been focusing on the fastest jet stream winds, which are at the upper levels, this 9 to 16 kilometers above our head. And so what was new and important about our work was that we tapped into a different way of affecting density that turned out to be even more important at upper levels. And that is how, when you warm the planet, you instigate something called the water vapor feedback, which is to say that warmer air holds more moisture. And this is quite an important effect that is nonlinear. So it increases like an exponential curve. And so a small change in temperature can have a big effect in moisture. And this is well understood for the global average. What our work showed was that you can connect this to the jet stream, because if you go back to our contrast, when you think about the tropics, again, it's hotter and it has more moisture to begin with.
Mhm.
And the poles are very cold and have very little water vapor. It's very dry. And so when you warm those two regions, let's say together as a thought experiment, you're going to exacerbate that difference. Because for each degree of warming, you can hold that much more water vapor in the tropics where it's warmer to begin with, whereas you don't get much bang for your buck when you're talking about the polar regions where you're just so dry to begin with,
Mhm.
it doesn't really matter. So this has an effect on density, which is this contrast that's so important, because when you add water vapor to the air, you make it lighter, and that's maybe not something that's well appreciated. But if you just think of your standard periodic table, which maybe you don't remember, except in high school, even I don't use the periodic table every day.
Yeah.
The water vapor molecule, 2 hydrogens, 1 oxygen, is 18 on that table. You add up the values, whereas the air in Earth's atmosphere is predominantly nitrogen and oxygen. You add up those and you get 29. So the more water vapor you put in the air, the lighter you make it. And this whole story then comes together by saying that you're really lightening the tropics more than the poles. And what we showed in our research is that this is an even larger effect, in part because of this exponential dependence of water vapor, that at upper levels, where the jet stream is the fastest, it can dominate over the density changes due to the warming of the Arctic.
So is the upper levels where these flights, international flights, are taking place?
Exactly. When we talk about the core of the jet stream, where the fastest winds are, this ribbon of air, it's up at those altitudes, 9 to 16 kilometers. There are jet streams lower down. They're much, much weaker, but they are there.
I put up a graphic from your research, Dr. Shaw, and just to let everyone know, I added the red arrow to show the trend. So it's not an exact mathematical linear trend there. But do you want to talk about that figure?
Sure. Yeah, I think, the most amazing thing about being a climate scientist is the signal, right? So we can deduce the signal, we can try to understand it, and then that's really the starting point for going to look for it. So as we were unraveling our research with not only asking the question, but trying to explain and think through why there might be a change in the fastest winds, then we can go look at the data. So the black line shows a representation of the jet stream that we observe. And so it's showing the different values of the fast winds relative to the 1980 to 2000 period. So it's a percent. So we've normalized it by that time period. And so that black line is showing, of course, there's a lot of fluctuations. This is the noise, okay, that's on top of the signal, which is represented by the red line, which is mostly being guided by the other colors, which are these model predictions, these physics-based model predictions of how the atmosphere, the jet stream, responds to these increases of greenhouse gases, predominantly carbon dioxide. And so what you can clearly see, the black line, of course, stops in around 2022, which was the last full complete year we had when we did this work. But the colored lines continue because that's the prediction. But in both cases, you can see this tendency. Now, as climate scientists, we're often very conservative. We want to say we want multiple lines of evidence. We want to say when does the signal really emerge from the noise, and using those very high standards of signal to noise and emergence. The calculations we performed would suggest that this kind of signal of fast winds getting faster due to climate change would emerge from the noise in the middle of the century. So a little bit later for that very kind of clear signaled overwhelming, the fluctuations of day-to-day weather.
Mm-hmm.
So this is not going to just be a one-time occurrence. This is something that we're going to continue seeing, these faster flights.
That's the key point,
okay.
Right? Climate change is this like red line. And then we have, of course, all of the noise on top of it. But, the signal emergence from the noise as the red line is continuing to increase. Of course, one important issue is that we are in the driver's seat. So this signal increases if the more global warming occurs. Of course, if we curb our emissions and we do those sorts of things, then we can bend the curve, or we can change the curve.
Which is a great point, because I actually, one of the things that I asked Jeff when we were talking about this, I said, well, does this mean that airplanes are burning more fuel if they're getting there an hour?
Less, because you're the tailwind.
Because you also explained inertia. So we have all this force, right, kind of pushing towards all this wind helping the airplane.
And then I reminded her that sometimes you take return flights.
Right.
So there's some flights that have to go the other way. They're burning more gas.
So then they have to, right?
Yeah, exactly.
Yeah.
Yeah. So people don't, really appreciate the jet stream affects us in many ways. We fly within it.
Yeah.
It takes us longer if we don't have a tailwind. The jet stream, steers weather systems, low pressures that live off of the jet stream and interact with it and their frontal systems. And one of the things that we're looking at in follow-up research is going all the way down to severe weather, because one of the things that has been connected to these very fast winds, especially over the United States, is what they call severe weather occurrence, where when you concentrate the winds in these very, very narrow regions in the spatial dimension, it can generate upward and downward motion. And once you allow for upward motion, you can begin to instigate some of these thunderstorms and really severe convective outbreaks. And being able to kind of connect our research to that is something that we're actively working on.
Very good. So I have another question for you. So we talked a little bit about it. We can't get into any more detail in terms of the difference between, potentially a jet stream that's a little bit weaker, closer to the surface, but potentially stronger way up there. But I think it's an important point to make to everyone watching. Hey, they can both be true at the same time, but just at different levels, different latitudes, and also I would say different synoptic patterns, overall climate patterns that may be present at that time. But beyond that, I think folks would be interested in, I don't know if this is new wheelhouse, but maybe you can talk a little bit about it. Turbulence. We've seen the research on clear air turbulence increasing dramatically, especially over the North Atlantic. Do you have anything to add when it comes to the connection between turbulence and climate change?
So yeah, this is another one of those cases, I think, of unraveling the signal and why it's there, where to look for it, and how large will it get. And so this has been another fascinating story about the jet stream that involves what we call clear air turbulence, which is known to be connected to the jet stream changing its strength, because it's a ribbon of air, but it varies, as we've already discussed, with altitude. As we move upward, it gets stronger. And pilots are well aware that when the jet stream starts to do that, not only in the horizontal, but in the vertical, it can create turbulence, which is, just think of it as, whirls of air. The air is changing directions, and that's what leads to this, incredibly dangerous types of situations where people are being jostled around in an airplane,
Yeah, it's scary.
I don't like
tens
that
of
at all.
thousands of feet above ground.
Mhm.
Yeah.
And so the connection to our work is certainly that it's very complementary. Some of these contrasts that we are investigating for jet stream strength and that getting stronger and fast winds getting faster is also connected to what controls these jet stream variations and their strength with altitude. And so the same density contrasts are important in both cases. And so I think, again, giving us confidence as we unravel these stories, this understanding. I think the exciting thing with the shear is it's the turbulence is it's seems to be even stronger than the questions of why just over the North Atlantic, I think, are an active area of research for many of us in the community.
So listen, Val, just one more question because it's almost 3 o'clock.
Yeah. Are you going to test me on the?
No. I just want you to ask the last question. I want you to have the last word.
Oh, I thought you were going to. I was prepared to tell you what Coriolis was, but I guess that we're not going to do that.
I'll test you after.
Okay, sounds great. Actually, I'm looking at all the Facebook. We have some great comments. Seems like there's no questions on here, so I think that Dr. Shaw did an amazing explanation of what's happening. And no, I think she answered all of our questions. Do you have a last one?
I would just say that this is a big topic. People want to know why they're being jostled around these planes more often when it comes to turbulence. And also, I think it's inherently interesting, and it always gets big news when a flight is, over 800 miles an hour and it's challenging records. And, we might have at least part of the answer here, which is that a warming climate can, in certain circumstances, produce a faster jet stream. Would you agree with that, Dr. Shaw?
Yes, I think we are exactly, that's what we're on the hunt for. And I think what's exciting is that, we're seeing the signal and we can kind of test our ideas and kind of, in real time, learn more about the atmosphere and the climate system.
Great. Is there anything else that you want to add before we close?
No, thank you very much for having me. I really appreciate the importance of trying to communicate these topics. So thank you for your show.
Well, I'm glad that you were able to make it on. And I'm going to put the article up. There's a short article on our website, but it does link to Dr. Shaw's work if you want to read it. It's called Jet Streams May Be Speeding Up, and we're talking about the science behind it. So go to the WFLA webpage. It should be on the homepage. But if for whatever reason you're listening to this a couple of days from now and it's not on the homepage anymore, go to the weather tab and then click on Climate Classroom and you should see it there. So just one more time, I'm going to bring my guests up. Dr. Shaw and Val, thank you so much for joining me. And I want to thank everybody at home for joining me as well for Climate Classroom. We'll see you again next week or the week after, and we'll talk about another exciting climate topic. Thank you very much, everybody.
Thank you so much.
Watch or listen to Jeff's Climate Classroom, powered by Armor View Window and Door on WFLA social media platforms, and find Jeff's climate reports on WFLA.com.